Hello, everyone. Today I'm here to present our conversational agent, which we developed for climate-related questions and answers. This agent was developed by the Future Computing Group at the University of Oulu. This project is funded by the European Union. We use advanced architecture with multimodal retrieval, including vector databases, graph knowledge, and social tipping point analysis to provide accurate and contextual responses to climate queries. Currently, the bot works with 4 different EU languages: English, Portuguese, and Greek. In the upper right corner, there's a menu button. From there, users can select their preferred language from our supported languages. We support English, Italian, Portuguese, and Greek. We also have 2 reading modes, Easy Read and Advanced Reading. We've designed our system to accommodate different user expertise levels. Users are divided into 2 reading groups based on their preferences. The Easy Read mode provides simple, accessible responses that anyone can understand. In contrast, the Advanced Reading mode delivers more detailed, technical responses with scientific depth for researchers, students, and professionals in the field. Now, let's see the system in action with our first query. I'll ask a question about aquaculture production percentage in the Mediterranean and Black Sea region. As you can see, the bot has provided a precise answer to my question about the percentage, returning 91.3%. After each response, users can view all the reference documents that the bot consulted to generate its answer. Each document is ranked according to its similarity score, showing how relevant it was to the query. This transparency allows users to verify the sources and explore the information further. Users can click on each document to visit the original source and verify whether the bot provided an accurate response. Here we can see that the bot has extracted the correct answer from this news article published by the FAO. For each response, we provide 4 interactive buttons. Users can copy the response to their clipboard for later use, and they can also use our speech synthesis feature to have the response read aloud.
Over the past decade, marine and brackish water aquaculture production in the Mediterranean.
We also have thumbs up and thumbs down buttons to collect user feedback about the bot's performance for further research and improvement. The system tracks all feedback interactions, allowing us to continuously refine the bot's accuracy and usefulness. Each response also includes social tipping point analysis. A social tipping point is a critical moment when a small change in a social system triggers a rapid and widespread shift in attitudes or behaviors, leading to significant, often irreversible societal change. To generate these social tipping point insights, we developed a specialized pipeline that identifies and analyzes these transformative moments from relevant literature and data sources. This feature helps users understand the potential for large-scale behavioral and social transformation related to climate and environmental issues. Right after the social tipping point, we also display 5 key factors that we considered to determine whether this content represents an actual social tipping point or not. These 5 factors serve as our evaluation criteria, providing the rationale for why we identified this particular insight as a social tipping point. This transparency helps users understand the reasoning behind our classification and builds trust in the system's analytical capabilities. Additionally, if the response does not contain any social tipping point insights, this section will clearly display a message indicating that there are no social tipping points identified for this particular question. After the reference section, users will find a continuous conversational input box where they can ask follow-up questions and engage in an ongoing dialogue about the response. The bot maintains conversation context, allowing for natural multi-turn interactions. For example, I can ask a follow-up question like, "Where was the conference held, and how many countries participated in the discussion?" It's important to mention that we have a query preprocessor working in the back end. For conversation-starting questions, the system simply corrects grammar and sentence structure errors. However, for continuous questions, we perform a more sophisticated analysis by examining both the current question and the conversation history to resolve pronouns and unclear references. For example, in this conversation, the initial question was, by what percentage did marine and brackish water aquaculture production increase in the Mediterranean and Black Sea region over the last decade? And the follow-up question is, where was the conference held and how many countries discussed it? The preprocessor identifies the pronoun it and replaces it with the appropriate context from the previous question, transforming the query before retrieving documents from the databases. And also here we also fix the grammar and sentence structure errors. This pronoun resolution is crucial because without the right context, we cannot retrieve the correct data from our knowledge base. As you can see, the bot understood my follow-up question and provided accurate information. It identified that the conference was held in Greece and had participants from 30 countries attending the event. You'll also notice that when I ask follow-up questions, the previous references are hidden under a collapsible button to maintain a clean, organized interface for users. If users want to review the references from an earlier response, they can simply click to expand and see all the source documents. Now let me ask a completely new question, unrelated to the previous conversation. I'll ask, what is carbon emission? As you can see, the bot provides a clear answer explaining that carbon emission is often referred to as CO2 emission. On the right side, you'll notice the social tipping point analysis related to the carbon emission query. Below the social tipping point section, there's an Explore button. When users click this button, they are taken to the knowledge graph we've developed, which provides a visual representation of interconnected concepts and relationships. This is the knowledge graph representation of the response. Here we can see how different entities are connected to each other and how relationships are built within the climate and environmental domain. This visual network helps users understand the complex interconnections between concepts, actors, and phenomena in climate science. This is a highly interactive knowledge graph. Users can click on individual nodes to explore specific entities and their connections in greater detail. When users click on a node, it displays a brief description of that entity. You can also see how many organizations, people, and events are represented in this knowledge graph, providing a comprehensive overview of the interconnected, climate-related information. Users can also zoom in and zoom out to navigate different levels of detail within the knowledge graph. They can also switch to full screen mode to get a better viewing experience and explore the relationships more thoroughly. There's also a detailed visualization option where users can switch to 3D mode for an even more immersive experience. In 3D mode, users can see a three-dimensional visualization of how each node and relationship connects, offering a spatial perspective on the knowledge structure. This knowledge graph is generated from the first reference document shown in the sources for each response, ensuring that the visual representation is directly tied to the most relevant information retrieved. Now let's test the chatbot with a query that might not be in our knowledge base. I'll ask about the ENSO cycles. As you can see on the left side, the system displays a clear disclaimer stating, "I didn't find any specific documents in my knowledge base for this query. I'm providing information based on my general training about climate and environmental topics." Essentially, the bot acknowledges that it doesn't have specific information about this particular query in its specialized knowledge base. However, instead of simply refusing to answer, it provides general information based on its underlying language model training. Each conversation operates within a session that has a 10-minute inactivity timer. If there's no user interaction, the system begins a countdown from 10 minutes to 0. Once it reaches 0, all session data is automatically deleted to ensure GDPR compliance and protect user privacy. As you can see, when I move my mouse or interact with the interface, the timer resets. However, if there's no activity, the countdown begins. Users also cannot refresh the page as it immediately clears their data and redirects them to the home page. Similarly, when the automatic timeout occurs, users are redirected to the home page as well. This design ensures that sensitive conversation data is never stored longer than necessary, maintaining strict privacy standards. This is our RAG pipeline architecture that powers the backend. As you can see, we start with the user query. For example, what is climate change? We use a parallel retrieval approach, which means we simultaneously retrieve data from 3 different sources: document chunks and summaries from Milvus Vector Database, and graph data from LanceDB Graph Database. Then all retrieved data is then sent to a re-ranker model, which ranks the documents by relevance and filters out unnecessary information. This re-ranking step is crucial. It significantly improves response quality by ensuring only the most relevant information is passed forward to LLM. Finally, we send the re-ranked, filtered data to the large language model to generate the final response. This is our social tipping point identifier pipeline. First, we retrieve all documents from S3 storage, which we're using with MinIO. Then, we send the data through a PDF extraction process to get all the text content from the files. Next, we remove all references and citations, particularly from scientific papers, to focus on the core content. We then perform basic text cleaning, fixing spacing issues, word breaks, and punctuation errors. After cleaning, we apply a hybrid chunking technique to split the documents into manageable chunks. We then use a trained classifier model that we developed using a dataset provided by the EU consortium. This model achieved over 80% accuracy in identifying whether a chunk contains a social tipping point or not. Once potential social tipping points are identified, we use an LLM to refine the text and make it more readable for display in our interface. The LLM also generates the 5 qualifying factors that explain why this particular content was classified as a social tipping point. Finally, we upload all this processed data to Milvus Vector Database, where it can be retrieved using semantic search when users ask questions.